In Chapter 8, we look at drawing conclusions from a large sample. And first of all, statistical inference deals with drawing conclusions about population parameters from analysis of the sample data. And parameters we talked about before, such as the average, or you can say mean, or standard deviation, or variance. And so we want to know population parameters. So for example, population average. So if you want to find out the average height of the entire country, and so that's population mean. But again, it's very difficult to find the height of everybody in the whole country. So what we do is we use the sample data and find out the average, which is the sample mean, and then we use the sample mean and we try to get a conclusion. And we talk about how close the sample mean is to the population mean. So the example we talk about is the community service hours in a month. So if we want to find out the community hours, service hours in the past month of the say the average number of hours of the students and community service in the whole university. And if we have 2,000 students or even more, maybe for a big university we may have like 10,000 or 20,000 students, and it's very difficult. It takes time to do that. So what we do is we're gonna find, say, 40 students, and we can find out the average number of service hours for these 40 students. But does the answer represent, can we use the answer to represent the population mean, the average numbers of hours of the whole university, and how good the answer is? So this is what we discuss here. And the point estimator, so we use the sample mean as estimation of population mean. So the sample mean can be called a point estimator or just estimator. And the standard deviation of estimator is called its standard error. So what we when we find out the sample mean, we can also find out when we find a sample mean, we can say sample average, we can find out the average of the average, and we can also find out the standard deviation of the average, and that is called standard error. And this picture here shows what we talked about before, central limit theorem. X bar right here, X bar means the average of something, and we know the picture, the X bar is approximately normal distribution. So the probability, this is the probability density function. If we want to find the probability, that's the area under the curve, under the probability density function. So for example, the shaded area here, the area is equal to 0.954. So that's about 95.4% of the entire area under the curve. And that means the probability, the chance of the average falling into this category from left point here to the right point here is 95.4%. Okay, so you can say we are 95.4% confident that the average we found, the sample average, the sample mean, is going to be between this number and that number. Okay, but the population mean, mu, that's population mean, is what we really want to know. So the population mean is, for example, the average number of hours, community service hours for the entire university, all the students in the university. And but what we can get is only the sample average. So the sample, but we know from the picture, we're 95.4% sure that the average number is going to be falling into this range from here to here, near population mean. So it's not so far away from mu, and 95% sure it's pretty good. If you want it, but this how confident do you want to be? It really depends on the yourself, how accurate the data has to be. So if you want it to be 95% sure, and you can see it's marked here, it says 2 delta divided by square root of m. So that we know from previous chapter, we know that sigma divided by square root of n, sigma divided by square root of the sample size, that is the standard deviation of x bar. So if you take 2 standard deviations of x bar, your number can be 95.4% sure, certain. So if you only want to be 80% sure, so the range will be smaller. Will be that you just want the area under the curve to be 0.8. So of course the area can get smaller. And if you want 99% sure, then you have to increase the area under the curve. So the range will get bigger. Okay, so that's just a little bit background about this chapter. So we want to use x bar to approximate mu. So or in other words, we say we want to use sample mean to approximate the population mean. And what is the error margin? So we want to find out the error margin. And of course, the error margin really depends on how confident you are. You can say I'm 95% sure, then the error margin will be from here to here. Because x bar could be anywhere from here to here, and mu is always right here in the middle. So the error of x bar will be from, if say the worst case x bar is right here, so the error will be this distance from mu, or x bar could be here and the distance from x bar to mu would be this. So that's exactly 2 standard deviations. And of course the error could be smaller. X bar could be right here. So if x bar is right here, then the error is only this much. Or maybe x bar is right here. So when x bar gets closer and closer to mu, the error is very small. But the error margin is, the worst case is right here. So this is called the error margin. And from the picture we know the error margin again depends on how confident you want. If you want 95.4% sure this is the area under the curve, so it's 0.954, and you need to have 2 standard deviation. But if you only want if you only want to 68% sure, and from the previous chapter, so the area under the curve is 0.68, and then you can be this. The error could be this close, and then the error margin is the range is smaller. Okay, so we can look at the formula is right here. So the error margin formula is z half of alpha times sigma divided by square root of n. And the sigma, we know sigma divided by square root of n, that is 1 standard deviation of sample mean, multiplied by z half of alpha. Z half of alpha tells you how many standard deviation do you want. It's either 1 standard deviation or 1.5 standard deviation, 1.6 standard deviation, or 2 standard deviation, 3 standard deviation, whatever. So this value changes, z half of alpha. Sometimes we call it the z score, this value, and this value depends on the percentage. So you want how confident you want it to be. And in the formula sigma, sometimes we use S, that's the sample mean, instead of sample standard deviation instead of population standard deviation, because sometimes this data standard deviation, population standard deviation is not available. We can use sample standard deviation. So we can look at the example we talked about before, that if we have surveyed the 40 students, and we found out the average number of hours of community service of these 40 students is 4.55 hours, and with the standard deviation 5.17 hours. If we say we want to be 95% confident about this, the population mean, of course we use 4.55 to use it to approximate the population mean, that is the average number of community service hours of all the students in the campus, and we want to find out the error margin. So what's the biggest error you're gonna have, the distance from the actual population mean to your sample mean. We apply the formula, we find out it's 1.6 out. So when we use the formula, 95% error margin, so that means the area under the curve is 0.95. So the area under the curve is 0.95, and which is approximate 2 standard deviation. And we can use this table right here, 95% sure. So this 0.95, the corresponding z-value 1.96, so you have to do 1.96 standard deviation, almost 2 standard deviations. So we take 1.96 for z-value here, z-score, times sigma, population mean, standard deviation is not available, we use sample standard deviation 5.7 to replace it, and divide by square root of the sample size 40. So 1.96 times 5.17 divided by square root 40, and you can use calculator to find out it's 1.6 hours. So this 1.6 is the error margin, 95% error margin. In other words, it means that we are 95% certain that the distance from the average you found to the real population mean is 1.6. So this number is, you can say, well, how good this number is. So the worst case is you add 1.6 or subtract 1.6. That is going to be the actual population mean. But and of course, that's, you are 95% confident. You will never be 100% confident. You're, I guess usually the best is 99% and confident. So that is how we found error margin. So what you need to do, it's very simple. Just apply the formula, and the percentage number, you apply it to get the z-value, z-score, and times the sample standard deviation or population standard deviation, depending on which one is available, divided by square root of the sample size. And the other formula we have is for the sample size. Suppose I want my error margin to be a certain number. Say, for example, I want the previous example, I want the error margin to be 1.6 hours. Actually, I can say I want my error margin to be smaller than 1.6. I want it to be 1 hour, or maybe 0.5 hours. And then you have to determine the sample size. Okay, so what I did is I just did I want my error margin to be less than 1.6 hours. I can actually, this number you can change it to any number. I can change it to any number, and then when you change this error margin, then your sample size may change. So I use the formula, and I explained in class how to get this formula. So I'm gonna skip it here, and let's just show you how to use the formula to find the sample size. So the sample size, plug into the formula, z half of alpha. Again, you are 95% sure. So the number using the table one more time here, 95% sure it's 1.96, and then 1.96 times sigma, which is not available, so we use 5.7, and then divide by d. D here means error margin, which is 1.6. So divide by 1.6, and then take the square, you get 40. So actually you get about like 40.08, but so sample size is about 40. And so if I wanted it to be, say, 1 hours, is less than 1 hour, what I have to do is I just change. So this is one. If this is 1 hour, I just change this to 1 hour, and then I can use calculator to find out 1.96 times 5.17